Hello class, I am your substitute teacher for the day. My name is Albert Einstein. Please throw away your books. Today we are going to be learning about relativity.
Aren't we supposed to be learning our times tables?
No, this is much more interesting because I came up with it. Hit it! Today I will be teaching you relativity. Two series I proposed consecutively. I understand it's not in the primary school curriculum, but if I teach it to you creatively, basically you'll understand everything, at a minimum. I think we require a change of setting. Follow me into this rocket ship, and while we are getting to where we are going, I'll give you some history, fill you in with some terms before I walk in with relativity. These two people are renowned, their work all proven to describe the physics of our universe, and to Galileo and Isaac Newton. Their definition of relative is important to describe the motion of any object. Let me show you this by looking at our spaceship externally. You cannot say that we are moving with any certainty unless you compare us to that planet we just flew past. Compared to that, we are moving very fast. We call that planet a frame of reference. On Earth, the ground would usually be our first preference. A car might be going fast compared to the ground, but compared to another car, it isn't moving around. An inertial reference frame is one that is not speeding up or slowing down. The second important precursor to relativity is light. Scientists have proven that it always travels right at 300 million meters per second. It never changes, so then along came me, and what I said next was outrageous. I propose two statements. The laws of physics are the same in all inertial reference frames, and the speed of light is constant for all observers. It doesn't change. These make up special relativities. The special is there because it only describes the motion of a vessel that isn't accelerating or influenced by gravity. We'll come back to these later when I discuss general relativity. These two statements might sound simple, but the implications might just blow your mind a little. Special relativity applies to situations where things are moving really fast. In these occasions, more than 20% of the speed of light. Right. Our normal understanding of physics is that distances are the same. A 30 centimeter ruler remains 30 centimeters always, and time doesn't change. It ticks on at the same rate wherever you are. Great, but this isn't the case. Let's go up to the top deck in space. If I take this mirror and this laser, as well as two slow motion cameras, one here and the other on that planet, I shine my laser at the mirror and then look at the footage we captured, first rewinding backwards. The light travels to the mirror and back again, totaling a reasonably small distance, and then let us look at the footage in the camera on that planet. The light travels towards the mirror, but the mirror was in transit. So relative to the planet, the light traveled further than relative to us. However, as the speed of light doesn't change, time and distance must. Because we are moving so incredibly fast, time is ticking slower for us than on that planet we passed. The concept that time and distance are changing lumps space and time into one single thing, creating the idea that space is four-dimensional. It's called space-time, and space-time is flexible. Earlier I mentioned the flaws in special relativity, acceleration and gravity. So 10 years later, I published a new theory. General relativity. The universe will never be the same. We get to discard inertial reference frames and look at things that are accelerating, as well as gravity, accommodating for the universe to be explained by that four-dimensional spacetime that we earlier entertained. First, in 1907, I had my happiest thought, that a man in free fall's fate would be naught. Conversely, if our spaceship accelerates upwards in reality, we feel as if we are under the influence of gravity. We can show this weightlessness of freefall with a bottle full of water that is covered in holes. Gravity pulls the water down, causing the bottle to spout, but as it falls, the water stops falling out. Here I model spacetime with this stretchy fabric. This shows what we found earlier. Spacetime is elastic. However, we find that the thing that warps spacetime is mass and gravity. That is the main idea of general relativity. Objects with mass have gravity. This planet pulls on us because it is so massive that its gravity is strong enough to hold us down, and gravity is all around. This light little marble doesn't have much mass, so it travels across space-time, skimming past, but a big hefty object, the sun, is more massive, so it warps space-time and pulls things towards it. Next, we can put things into orbit. Note that as they get closer, the bubbles get faster, but they can't get faster once they hit the center. Now what if we have at our center a star that has the same mass but is smaller by far, and eventually it gets so small that it takes up no space at all. When a star collapses, it forms a black hole which sucks more and more mass into a space that's infinitely small, accelerating everything so fast that even light can't escape. That is why it has a black center and forms this shape. Now everything tries to travel in the straightest line it can, but as space-time is bent, even light bends around the black hole span. So most galaxies exist around black holes, much like the sun's role. The coolest thing comes with what we learned earlier today, that something going really fast experiences time at a different rate. So if you fell into a black hole, it would accelerate you to be so fast that it would look like you were falling always. And you would see the entire history of the universe flash before your eyes. So what did you learn today?
You can only say that you are moving relative to a reference frame.
The laws of physics are the same in all inertial reference frames.
The speed of light is always the same, and space-time bends to accommodate this change.
Mass bends space-time, and black holes are so massive that they collapse in on themselves to be infinitely small, bend light, and accelerate things to the speed of light. Good. Class dismissed. Oh, by the way, we went so fast in our rocket ship that it is now the year 2100. I'm off to teach the violin.